So yeah, so it's question 6, November 2021 question paper. Let me just zoom in a bit. Then like the first question, they say question 6, they say consider the balanced equation below for a hypothetical reaction that takes place in a 2 decicubic meter container at 300 Kelvin. So we have the equation P, which is a gas, plus Q, which is also a gas, is at equilibrium where the products are 2pq. And from the equation, we can see that it's balanced, because that's the first thing we must check. It's balanced. There's 2p this side, 2p this side, and 2q this side, and 2q that side. So the first question is define chemical equilibrium, but we're just gonna skip through that because it's not really necessary. So we're gonna get into 6.2, where they say the amount of substance present at equilibrium at 300 Kelvin is shown in the table below. So this is the number of moles at equilibrium, because they say amount, which is in moles. So we have 0.8p at equilibrium. We have 0.8q diq at equilibrium, and we have 3.2q pq at equilibrium. So they say the temperature of the container is now increased to 350 Kelvin. When the new equilibrium is established, it is found that 1.2 moles of P is present in the container. So they are going to ask, is the heat of the reaction positive or negative? So from this information, when they say the temperature is increased, is the heat of the reaction, like just the forward reaction, is the heat of the forward reaction positive or negative? What do you think?
So I think it's positive.
Positive of the forward reaction.
It says endothermic on the left and exothermic on the right.
Yeah, so since you said let me just get something to draw here. You said it's endothermic to the left, right? And exothermic to the right. That means to the right, the heat of the reaction is going to be negative, right? Then to the left, the heat of the reaction is going to be positive. Because as the temperature increases, the equilibrium is going to favor the endothermic reaction. So that's why when the temperature is increased, the number of moles of P is increased. So the forward reaction is going to be exothermic. And the reverse reaction is going to be endothermic. And so do you understand that part?
Yes, sir.
Okay, so I think like you got it, like from your answer, you have a good understanding of the situation. It's just that maybe you you mis you misunderstood about the heat of the reaction. But anyway, let's move forward to the second one. And they say 6.2.2, they say use Le Chatelier's principle to explain the answer. So I basically explained it using Le Chatelier's principle because I said when the temperature is increased, the equilibrium is gonna favor the endothermic reaction. Thus, the amount of P is gonna increase from the amount of P at equilibrium is gonna increase from 0.8 moles to 1.2 moles. So that's basically how you're gonna explain it using Le Chatelier's principle. You understand that part?
So do the reactants increase?
Yeah, the reactants increase. Because the reverse reaction is endothermic.
So I'm confused. Because when the temperature increases, only the products increase.
No. When the temperature has increased, the reaction, the equilibrium is gonna favor the endothermic reaction. And when the temperature is decreased, the equilibrium is gonna favor the exothermic reaction. You understand that part?
Yes, sir.
So in this situation, they tell us that at the first equilibrium, which is at 300 Kelvin, right? The amount of moles of P is gonna be 0.8 moles, right? But now the temperature has increased from 300 Kelvin, from 300 to 350. So the endothermic reaction is going to be favored. And that's why the amount of P has increased from 0.8 to 1.2 moles. That means the reactants are going to be favored. So there's going to be more reactants now and less products. Does that make sense?
Yes, sir.
Okay. So don't be afraid to stop me if you don't understand. Then now they say calculate the equilibrium constant at 350 Kelvin. So if you remember from Sunday, let me just try to find space here. Let me just switch off my phone. Where can I get? Let me try to see if I can get a plain sheet. Okay, let me scroll down. Yeah, let's just use this part right here. So this is in page 15. So now we're gonna have to collect our data first. So before we can find KC at 350 degrees. So firstly, we need to know our equation for Kc. So Kc, it's gonna be the concentration of the products, the exponent of the coefficient of the products, divided by the concentration of the reactants to the exponent of the coefficient of the reactants, right? So here we know that our number of moles at equilibrium is gonna be 1.2 moles. So we're gonna have to relate this data to the newly found data right here. So from this information, we know that from the equation, we know that 2p is how do I say this? The ratio of p and q, it's 2:2, which is gonna be 1:1. So let me just go back to that page and draw that table. Page 15. So we're gonna have our table right here. Then this is gonna be our initial, but this time, instead of using the concentration, we're just gonna use our number of moles. So don't get confused when like I'm gonna use initial number of moles, change in number of moles, and the final number of moles. Okay, so it's just gonna have a line here and another line here. So now we have our equation, which is 2p plus u2 is at equilibrium with 2pq. So we know that at equilibrium, which is our final the equilibrium is the final conditions. So let me just change this final. Let's just change this final from final to equilibrium. So this is going to be the number of moles at equilibrium. So from the information we're given that the number of moles of P at equilibrium is going to be 1.2. Let's go back to that. Then using ratios, we know that 2p is to Q. So we know that also for Q2, right? Q2 is gonna increase by the same amount. No, Q2 is not gonna increase by the same amount. Q2 is gonna increase by half the amount that P is gonna increase by, because the ratio of P and Q is 2:1, right? So Q is gonna increase. So this is gonna be 2 over 1.2 divided by 1 over X. Then we're gonna find this X, which is gonna be the number of moles of Q at the new equilibrium. So let me just write that to the side. It's gonna be 2X is equal to, when you cross multiply this, 1.2. You understand so far?
Yes, sir.
Okay. Where's the space again? So I'm just gonna write change is gonna be 0.6. So from the information, right, the initial conditions of the reaction, we know that this, the initial conditions, we know the amount of this is 3.2, because they gave them to us, they gave us the initial conditions in the table, right? So these are the initial conditions of the reaction at 300 Kelvin. So we're just gonna have to write this into our table. I think 0.8, 0.8, and 3.2. So it's gonna be 0.8 moles, and this is also gonna be 0.8 moles. Then this is gonna be 3.2 moles. I think I made a mistake using the ratio part to find the amount of Q2. So from now, let's just move on with the table as it is. I apologize for the inconvenience. So in order to find our change, the change is equilibrium minus the initial, which is gonna be the change in number of moles is gonna be the number of moles at equilibrium minus the number of moles initially. So that's gonna give us 1.2 minus 0.8. I think that's gonna be 0.4, right? Then you have to show the positive sign to show that the number of moles have been added and not lost. So it's gonna be plus 0.4 moles. Where's that? So when we get to here, that's where we can use that ratio. Where we're gonna see the change in number of moles of P is to 1 change in number of moles of Q. So yeah, I think I made a mistake there at first, but now this is the one that we're gonna use. So we know the change in number of moles of P, that's 2 into 0.4. So that's gonna give us the change in number of moles of Q, which is, let's just call it X for now. So our X is gonna be 0.8. Does that make sense?
Yes, sir.
Okay, so here we're gonna add 0.8 moles. So we add 0.8 to this 0.8, we're gonna get 1.6 moles at equilibrium. Then now we're also gonna use, through using the ratio, we know that the change in number of moles of P is equal to to 2 the change in number of moles of PQ. Then this is just gonna be 2x. Then the change in number of moles of PQ is gonna be is also gonna be 0.4. But this time, since it's a product and the product is getting converted into reactants, we're not gonna add the number of moles, but we're gonna subtract them. Because now we're gonna have less of the product, but more of the reactants. That's why we add on the reactants and subtract on the product. So now we're gonna have our number of moles of PQ at equilibrium is gonna be 3.2 minus 0.4. I think that's 2.8. It's gonna be 2.8 moles. of PQ at equilibrium, right? But the thing is, this is not the answer. This is not what we're looking for. But these units, these values here, are the values we're gonna use to calculate our Kc. But if you remember, I'm sorry, the equation states that it's concentration divided by concentration. So it's not number of moles divided by the number of moles. So I'm sure you're aware of this, but concentration is directly proportional to the number of moles and inversely proportional to the volume. So now we're gonna have to calculate the concentration of P, the concentration of Q, and the concentration of PQ at the new equilibrium. So we know that the reaction is sealed in a 2 decicubic meter container. So that's gonna be our volume. This is 10 minutes left. So let me just calculate the volume right here. So this is gonna be the concentration of P. That's gonna be equal to 1.2 divided by 2, which is gonna give us 0.6 mole per decicubic meter. Then the concentration of Q, that's gonna be, what's that number? What's that value? 1.6. Sorry. It's gonna be 1.6 divided by 2. So I'm just gonna write this unit once because just to save time. So just going forward, you should know it's 0.8 moles per decicubic meter, and also the next answer. So it's gonna be concentration of PQ. That's gonna be 2.8 divided by 2. That's gonna be 1.4. And remember, it's very important to write the equation. So before you get to all these calculations, you have to show that concentration is equal to number of moles divided by volume. So now we're gonna go into the Kc, the equilibrium constant. So Kc is gonna be concentration of products, coefficient of to the exponent of coefficient of the product, divided by the concentration of the reactants to the exponent of the coefficient of the reactants. So that's gonna be the product, that's gonna be 1.4. And from the equation, we know that P2P plus Q2 is at equilibrium with 2PQ. So the coefficient of PQ is 2. So this is going to be 1.4 to the exponent 2. You're going to divide that by 0.6, and it has a coefficient of 2 as well, so it's going to be to the exponent 2 divided by 0.8. So can you just quickly type this into your calculator? So what answer did you get?
So must I round off to 2 decimals?
Yeah.
So then I get 6.81.
6.81. So that's gonna be our equilibrium constant at 350 Kelvin. So since we have, let's just go through this for like 2 more minutes, then I'll start a new meeting. So do you have any questions concerning that equilibrium constant?
No, sir.
So you fully understand how the steps and how it's done.
So maybe not fully, but I don't know it.
Right? Let's you can ask me which part did you find most confusing?
So I think it was the ratio part.
The ratio.
Yeah.
Um
Because for you, I did you get negative 0.4?
as I said, when the temperature increased, the endothermic reaction, the reverse reaction was favored, right?
Yes,
So
sir.
since the products are, since the reactants are gonna increase, the products must decrease because it's at equilibrium. It's not like they're gonna add more. They're not adding more of maybe they're not adding more P. They're just increasing the temperature so that PQ can be converted into Q2 and P. So that means PQ is gonna lose its mass, and that mass is converted back into Q2 and P. Does that make sense?
Yes, sir.
So since it's losing its mass, you know that the number of moles is directly proportional to the mass and inversely proportional to the molar mass, right?
Yes, sir.
So since the number of moles is directly proportional to the mass, you know that when the mass is gonna decrease, the number of moles is also gonna decrease. So this negative is to just show that this is decreasing and these are increasing. You understand that?
Yes, sir.
So that's where the negative comes from. So do you have any more questions?
Yes. So does it decrease like directly proportional to the reactant?
Sorry.
So does the product like decrease directly proportional to the reactant? That's 0.4.
No. The product is always inversely proportional to the reactants. So when the product increases, the reactants are going to decrease. And when the reactant increase, the product is going to decrease.
So but I'm confused where the 0.4 is from.
Let me just since we have less than a minute, let me just stop recording.